If you think about soil and if you think about the built environment, everything started from the ground. Either you build a house, either you excavate, either you need to build a parking space, everything started from the ground. The soil is a very complex medium. You have an interaction between the solid particles, water, and then the air. And this interaction is changing depending on the type of problem that you have. In the Netherlands, we are basically surrounded by dikes and embankments. We have 14,000 kilometers of dikes that actually ensure that the Netherlands can survive from flooding. So the western part of the country is below the water level. Therefore, we rely, our society, our economy rely on this network of infrastructure. Assessing the safety of this infrastructure is quite important, especially nowadays in the context of intensification of climate stresses. In the past, the Netherlands was not used to this weather. We are getting periods of scarcity of precipitation, quite high temperature. It's a condition that the Netherlands was not actually experiencing in the past. And that is posing new challenges for our infrastructure and for our soil. A lot of these dikes are actually made or founded on very soft soil, especially in the western part of the country. We have soft clays and peat, which actually are soils that contains a high amount of water. And losing water, the soil actually shrinks. And upon wetting, when actually we have rainfall, this soil is not capable to regain as much as volume that it has lost. Understanding the dynamics of this process, which is soil-atmosphere interaction, is actually fundamental to ensure the safety and the serviceability of this infrastructure. What I have in my hand is actually a sample of peat, which is this very highly organic soil, very much present in the Netherlands, especially in this part of the country. You can imagine that the shrinkage of this sample, which means the loss in volume, could impact the height of our dikes. These houses are actually below the water level. So it's really important that we ensure that the height of the dike is almost stable in such a way that these people, and especially the infrastructure, do not suffer from flooding. And the data that we collect from the laboratory are actually useful to have models that can predict how much this material shrinks if outside we have 30 degrees or if there is a month of absence of precipitation. Fundamental to assess the behavior of the soil is measurements of the pore water pressure, which means that measuring suction, for example, with the high prop is fundamental if you want to describe what is the stress that the soil is experiencing throughout different stages of drying and wetting. And that measurement is essential for us to link the deformation of the soil, so the change in volume, the change in height, with the stress of the soil.
So one of the things we do over time is that we see how the pressures inside of the soil are generating and how the water is leaving, but also periodically during the testing, we can take the sample out and place it in this laser system that was developed here in-house in the TU Delft. The laser system allows us to monitor the volume of the sample in real time, and we will be constructing a 3D interpolation of the sample in time. Putting all of it together allows us to gather the data in the shape of the retention curve, and these type of curves we eventually put inside of the models we develop. Modeling and measurement are really not sequential tasks. These are things that feed on one another. By doing these measurements, we calibrate a bit the models. We also formulate new ways of accounting for the shrinkage or the sample change. And we put it inside these mechanical models. Then we check on a simulation, what are the predictions for a dike? What are the predictions for the maintenance, for the things that we should do? And sometimes those predictions are very in line with reality, and sometimes we still are missing some aspects. So that's where we go back and we have new questions to set up new experiments and to improve our models.
One of the most important characteristics of soils, in my opinion, is that the soil keeps memory of what is happening. When we move the soil from the field to the laboratory, we can actually see the history that this soil is experiencing when we perform laboratory tests. So performing laboratory tests implicitly accounts what happened in the soil in terms of drying, wetting, or loading and unloading. And that makes the data the fundamental point when you want to build a model on top of it. A model itself cannot take into account the history that this soil experienced unless you have data that tells you the history. So once the model has been validated, we can use the model as a predictive tool for simulating future scenarios. But the model must always be validated on laboratory data. That's why it's essential to use laboratory data and model together. There's two parts of the same problem. We can't decouple those two parts.